Alright, so today we're continuing our discussion of analytic functions. And today we are going to be kind of generalizing this notion to vector-valued functions. And we're going to start off with a definition here, where we have an open set in our field, m-dimensional, and we're going to let phi be a collection of components phi1 through phi n, which as a whole is going to send u to kn, each one sending, of course, u to I think it's an element of u to a specific component of that kn. Then phi is said to be analytic. If every component phi I is analytic. And so then this gives us a theorem, which we saw last time as a lemma, as a more specific case. We're going to suppose that f from u to v and g from v to w are analytic. Where we're going to say u is in km, v is in kn, and say w in kp are open. And then their composite is analytic. Alright, and look at our proof. So, for it to be analytic, we need a local power series expansion at each point in our domain, which is U. And now we've seen that it's a class of analytic functions defined in open subsets of some vector space based on K is invariant in their translation of domain or range. So we can assume, without loss of generality, let x be 0, f of 0 be 0, and g of 0 be 0. And we can just assume p is 1, and for higher dimensions, you just go dimension by dimension, component by component, and you should get the same thing still. So we're going to now let the sum for positive beta b sub beta y to the beta be a local expansion of g at 0 sorry, my writing is getting messy, at 0 valid in the strict polydisk around S, where we break S into its components as so. And we can break F up into its components, F1 through Fn, and we're going to look at an Fj, and we're going to let the sum over positive alpha of a 1 comma alpha x to the alpha be a local expansion of f sub j. We may choose R as a collection of R1 through Rm such that the sum for positive alpha of the absolute value of ai comma alpha times r to the alpha is less than si over 2. Then for h in p0 of r, well, then the composite of g and f of h is going to be the sum of beta positive of b sub beta, and where one particular component could be the jth component is going to be alpha positive of a sub I comma alpha times h to the alpha, and this whole thing is going to be to the beta. Now we need this right hand side to define a power series in H convergent in our strict polydisk of radius r. Now, I mean, it does define a formal power series in H because there's only finitely many terms which contribute to any given component. And so we need to check convergence. Which we get from my chair. What is happening to my chair even right now? The sum over positive betas of our b sub beta times the jth component being the sum of positive alpha. Alright, this is supposed to have more terms. Sum over positive alpha of a sub I comma alpha times h to the size of h to the alpha to the beta is less than or equal to the sum over positive beta of b sub beta of s over 2 to the beta is going to be finite. Which gives us our power series as existent. Okay, there's a remark here. I'm trying to parse it before I read off. There is a general method based off of the theorem of Ostrowski. Useful for such theorems. And we just note that we note that we can split into two cases. One where k is either real or complex, and one where k is ultrametric. Alright. So to illustrate it, we're going to go through the above theorem again with a more standard proof in this system. So we have our first case is where k is the real or the complex, and so we'll just, for our first case, we'll look at it to be complex. As we know that a function phi is analytic if and only if phi is C1 and d phi is a complex linear map. Since the composite of C1 maps is C1, the composite of derivatives is the derivative of composites, and the composite of complex linear maps is complex linear. We are done. And likewise for B, is going to be k being real. And once we have the complex case, the real one is pretty trivial. Which is, we may locally extend real analytic functions to complex analytic just by the local power series. And with that, we are done. We have the theorem. Now case 2. Here's where things get interesting. Where our k is ultrametric. Now, as in the original proof, we're looking for a power series of expansion of the composite of g and f about 0, with f and g of 0 giving 0. Now, without loss of generality, even further, we can replace gy and f of x by g of y over mu and mu times f of x over nu, respectively. For non-zero mu and nu in K. So we can choose mu and nu to make things easier. They don't really specify how as of yet. So we're going to let the jth component of G be equal to the sum for positive betas of b sub j comma beta times y to the beta be a local expansion of gj about 0. Now, you can choose S such that each G sub j converges in our polydisk around S. Now we can find a constant n such that for all j and for all beta, b sub j comma beta, its size times s to the beta, is bounded by n. Let mu be an element of K. Now, I'll write this on a new line, such that the size of mu is at least the max nj of 1 plus r n over sj. Then for all j and all beta, the size of b to the j comma beta over the size of mu over mu to the size of beta is at most the size of b of j comma beta times the minimum across j of sj to the beta times 1 over 1 plus n, which is at most b sub j comma beta of s to the beta times 1 over 1 plus n, which is less than 1. Hence, g to the y over mu has coefficients in the ring a sub v of the valuation v of k, of course. In particular, our g of y over mu converges in the unit strict polydisk. Now, applying the above, to mu times f, we can find nu and k such that the local expansions of the coordinate functions mu f of I times x over nu also have coefficients in A sub v. So we're reduced to the case where now the local expansions of the coordinate functions of f and g have coefficients in A sub nu. So the composite does as well. And so converges in the unit polydisk. So now we're going to look at some facts about differentiation and our Taylor series. Implicit in our discussion of the theorem that a conversion power series defines an analytic function. Start things off, we're going to look at a definition here. We're going to let phi be a function from u to v where u and v are open sets in k to the m and k to the n respectively. And we're going to pick some x in our domain. A linear function L from k to the m to k to the n is called a derivative of phi at x if there's two alternate ways to think about it. First off, phi of x plus h minus phi to the x minus LH is linear in h, is like its lowest term is being linear in the absolute value of h. As the size of h goes to 0, or equivalently, in probably the more familiar way, as we look as the limit of the size of h goes to 0, of phi of x plus h minus phi of h, phi of x minus L of h over the size of h goes to 0. And this is the same thing as above, just dividing both sides by this, by the norm of h, by the absolute value of h, not the norm. Okay. Remarks. If phi has a derivative L at x, L is unique, denoted d of phi at x. We also remark that if d of phi dx is applied to the vector with a 1 added component I and 0 everywhere else. The vector we obtain is denoted as essentially the ith component of the derivative of v of x. And this is our ith partial derivative of v at x. Alright. Now, to study the differentiability of analytic functions, it suffices first to restrict to analytic functions with values in k, and then further to functions given by conversion power series, since differentiability is local anyways. So okay, and then they go on to say they're going to use, for where I give ei being the vector within 1 in the ith component, they write it as delta I, so I'm going to replace mine to keep our notation consistent. So let's look now at a theorem they give us, which states, so we have f, b, a power series, convergent in the polydisk of radius r for positive radius. Then f is differentiable at each x in the open polydisk, in the straight polydisk of radius r, and it's weird, I don't know exactly how to. And they have that d of f of x. I think this is supposed to be a vector with its components being from delta of the ith of the first component of f of x down to delta n of f of x. So, and the derivative of an analytic function, I'm just going to write it like this. Function exists and is analytic so by induction an analytic function is infinitely differentiable. And the proof is pretty immediate. Just by a bunch of calculations from a little while ago that we did, where f of x was h minus f of x minus the derivative of f of x times a on h is a power series which is convergent in the open polydisk of radius r and of degree at least 2, with no terms, at least no terms of degree 0 or 1. Alright, and so we're going to decompose d alpha as d1 alpha 1 times through dn of alpha n? Well, first off, alpha factorial of delta to the alpha is just d alpha. Secondly, we have that the expansion of f of x plus h being the sum over our betas of delta to the beta of f of x times h to the beta is just the Taylor series in characteristic 0. And third is that alpha plus beta choose alpha times delta to the alpha plus beta is just delta to the alpha times delta to the beta. This gives us a new page where we are going to write the inverse function theorem. Let f be a function from u to kn be analytic, where u is open in k to the n, and without loss of generality, 0 is in u, and f of 0 is 0. Then this states that if df of 0 from kn to kn is a linear isomorphism, f is a local analytic isomorphism. In the proof, I hope you've already seen it for the real and complex case. So we're going to just let k be ultrametric. By following f with the inverse of df0 inverse if necessary, if needed. Without loss of generality, we can let fi of x be xi minus the sum over positive roots of positive alpha. we're not doing algebra anymore. Of a sub I comma alpha times x to the alpha, which is x to the I minus vi of x. Then replacing f of x with mu times f of x over mu, with the size of mu being large. As we saw before, we can let a of I comma alpha be in our evaluation ring for all I, and alpha. Now, to invert f, we need a convergent power series. We're going to call phi, capital Phi I of t such that xi equaling phi I of t solves the equation ti equaling xi minus phi I of x, as we saw from above. And there's two steps. First, we show that this has a formal solution, phi I, and we describe how the coefficients of phi I relate to our small phi of I. And we're going to show that this power series converges. So set big phi I to be the sum over positive beta of bi comma beta times t to the beta, and consider capital phi I. This is psi, I've been calling it phi. Psi of t being equal to ti plus phi of psi of t. Now we see from this that b of I and delta j is just 1 if I equals j and 0 if not. Now for arbitrary beta, we see that b sub I comma beta is a linear combination with positive integral coefficients of monomials in the coefficients of psi and phi of degree strictly less than beta. With these positive integral coefficients being independent of the psi and the phi. I said those in the opposite order, but it doesn't matter. Hence, by induction, we get that b of I comma beta is p sub beta to the I of a of j comma alpha, where p sub beta to the I is a polynomial with positive integral coefficients independent of the phi and it depends only on the a j sub alphas for alpha having a size less than beta. Now the first method we give to prove convergence depends on k being ultrametric. So by construction, b of I beta is in our ring of our evaluation for all I and beta. Hence, the CI converge in the unit, the strict polydisk of unit radius. This relies on the algeometric. Didn't even write the word on. Alternatively, we're going to look at Cauchy's method of majorance. And this holds kind of no matter what. This holds in like the real and complex case as well. Suppose that we can find a real positive power series as a collection of phi sub I, such that if the collection of psi sub I with this bar is the formal solution for the inversion problem for phi of I, phi bar of I guess I should be saying, then first off, phi bar of I being the sum for positive alpha, for alpha being at least 1 actually, of a bar of I and alpha sub I and alpha times x d alpha, and similarly phi bar of I being the sum over positive beta of b bar sub I and beta of t to the beta converge. And we have that the size of a of I and alpha is at most a bar of I and alpha, of course for all I and alpha. We then show that for all I and beta, we likewise have the size of b of I and beta be at most the b bar of I and beta, and we need to show this. And so, since the p beta to the i's have positive integer coefficients, we have that, I need a new line, b of I and beta is equal to the size of p beta to the I of aj alpha, which is at most the size of p, which is most p of the size of a j and alpha, which is at most p of a bar j and alpha, which is b bar of I and beta. So we just need to construct vi as desired. So for n being 1 and m being a positive integer, I'll illustrate that better if that's possible. N being a positive integer, a positive constant times phi bar to the m works. Where phi bar to the m is defined to be the sum over positive I of m times x to the I, where m is of course positive. And renormalize, we of course can renormalize. To assume the positive constant is 1. And we explicitly compute the inverse, which we're going to write as capital phi to the m bar, capital phi bar to the m of capital C, of phi bar to the m. And you do that by solving the equation t is x minus m of x squared over 1 minus mx. And our solution is phi bar to the m of t being 1 plus mt minus the square root of 1 plus mt squared minus 4 times m squared plus m times t. And this thing, that's why I did the square root last, because I know I'm going to mess it up once, because drawing with this tablet is hard. And this whole thing is over 2 times m squared plus m, which converging in a neighborhood of 0. Now for general n, take phi bar of I to be the sum over positive j of x1 plus through the xn to the j. And then the explicit solution, we have phi bar of I to be 1 over n times the sum for j distinct from I of ti minus tj plus phi bar to the n of the sum of our tj's over n. And then this gives us that the sum of our phi bar i's is n times phi bar to the n times the sum of our tj over n. Now our psi bar I, over phi bar I to the psi bar of psi bar is 1 over n times the sum for j distinct from I of ti minus tj. I guess technically j can be equal to I, plus phi bar of n to the sum of t sub j's over n minus phi bar to the n of psi bar to the n of the sum of our tj's over n, which is equal to 1 over n times the sum of our j distinct from I of ti minus tj plus 1 over n times the sum of our tj's, which is just ti. And since we know that phi bar of I converges to the neighborhood of 0, the theorem is proved. There's one more section, very short, but I think is important. I'm going to list here before we close off. My French is not good. Tellement dangereux is my best attempt at pronunciation. Because I know things get a bit messy, can get a bit messy in the algeometric case. First off, suppose K is algeometric. Our function phi as the identity, the indicator function on the ring of evaluation V is everywhere analytic. As AV is both open and closed, which I'm going to write as the ugly word clopen. Second, if K has a characteristic P, which of course is going to be greater than 0, for an analytic function phi defined on k to the n, and for alpha having a norm greater than p minus 1 to the n plus 1, then the alpha derivative of phi is going to be 0. Note that the radius of convergence of the derivative of a derivative may be greater than that of its parent. Thirdly, and finally, before we end off today's video, if phi is analytic on u and k to the n with an x in u and a p0 of radius r on x being in u, the local expression of phi at x may not converge, may not may not converge on all of the open of the stretched polydisk of radius r. This only holds true for the complex numbers. Yeah, I remember I worked through a book on p-adic analysis a while ago, and there's a lot of like ugly behaviors that can pop up with analytic functions in the p-adic case, so just watch out for that. Next time we're going to go into manifold theory, because like I said, Lie group is a group with a differentiable manifold structure, so we're going to kind of need to go through our differential geometry a bit again. I've taken a course on it before, but it's good as review anyways, right? Anyways, thanks for watching.